recording now. All right, so welcome to this second session, live session for the operating systems course. Let me share my screen. So today we are going to take a look at what the contents of the first two lectures from last week were. I hope you all watched the videos, and this was obviously quite introductory. So we started with the relations of the development, the history of computers to operating systems, how computers can be used, how computers can be used by multiple people. And then we took a look at very many basics, some of which you might know from a computer architecture introduction course, like how can we model a computer, which components are there, how are instructions executed, how does memory work, what are features of modern computers like multiple processors, memory hierarchies, and so on. And then very recent developments like using GPUs for general purpose computing, so not only for 3D graphics, and a bit about security and memory protection. So this is just an overview. We'll talk about many of these things in detail later throughout this semester, but just giving you a quick overview, I thought would be a good idea. So you get an overall idea of why we have operating systems and what operating systems are actually supposed to do. So we started with the question, what is an operating system? And this is an amazingly complex question because all of you have used operating systems before and are using operating systems. No matter which one, if it's Windows, Mac OS, Linux, one of the mobile operating systems, yeah, there is an operating system nowadays in every computer. So the question of what is an operating system is a bit hard to define. And we've seen many different definitions that go into different details, that go into different directions. Okay, there's a question asking for transcription. Yes, of course. And I've just cited two of the definitions here. And the first one already notices that it's actually hard to pin down what an operating system is, other than saying it's a software that runs in kernel mode. And even that is not always true. Now, if you buy an operating system today, or if you buy a computer that has an operating system installed, it's not just an operating system's kernel. There's so many other things belonging to an operating system. Nowadays, you have a web browser delivered with an operating system, maybe a database management system, maybe a video conferencing system. So it's a good question. Are these actually part of the operating system, or is this just a larger package, which we just call operating system just for convenience? Now, in this course, we want to concentrate on the core of the operating system itself. So what makes an operating system important and why do we need it? And obviously, you can use a computer that doesn't have video conferencing, though it's probably a bit more difficult in Corona times. But you don't want to use a computer maybe that doesn't have a file system. So we're looking at these very basic, very central things to using and operating a computer, which are required for almost every application. So there's another definition that defines an operating system, and we always abbreviate operating system usually as OS, just because we're lazy. So an OS is a program that controls the execution of application programs. So here we make a distinction between application programs like your text processing system, Word or something, your web browser, your chat client, and so on, and this other program, which we call the operating system. And this operating system as a program has the task of controlling all the other applications running on your system. And this is important. So if it needs to control them, it needs to have special powers. And to have these special powers, it needs to sit between the applications and the computer hardware. So applications cannot be allowed to have direct access to all of the computer's hardware. So for certain things in the computer's hardware, which we usually call resources, there needs to be a control about if an application is allowed to access it, how much of this resource an application can use. For example, can it use all of the memory in our computer or just a part of it? And other features, on the other hand, for these applications need to directly use the hardware. So instruction execution runs directly on the processor. The operating system doesn't have to do anything with it. But there are critical instructions like those which reset the computer, for example. Of course, an application program should not be allowed to reset a computer. So we need features, we need methods so that the operating system can actually control what the applications are doing, can constrain their operations, and can enable a secure and safe operation of our computer. And then, of course, we have different operating systems. So when we want to evaluate operating systems for certain applications, we can have some criteria, like the convenience of using it, the efficiency, like an operating system shouldn't use most of the computing resources for itself, or maybe also the ability to evolve. So if I have a new piece of hardware, will I be able to run my operating system and my old applications on this great new piece of hardware? There are many, many more definitions out there, and it's maybe a good exercise and a great idea. Try to define for yourself, what do you think an operating system is? What's your experience? And think about the others. That helps. It's a bit philosophical, obviously, but you see it's a wide field, and we're concentrating on the core matters here. So first, we took a look at the history of computers and of Norwegian computers. I don't go into detail on this, but in general, what we can observe is that the usage model of computers evolved along with their capabilities. So the first computers were very slow. They had very little memory, very little I/O capacities. So what people usually did on those was serial processing. So there was an operator. This operator received programs, so tasks, from the people who wanted to run programs on this computer. And then there usually was something like a paper calendar as a scheduler. So essentially you could reserve a time slot when your program should be run. You handed in your program, usually on a set of punch cards or paper tape or something like that. And then the operator took the next program, put it into the computer, started the program, waited until that program was finished or crashed, took all the data out of the machine, and started from scratch with the next job. This is obviously a waste of resources because the computer might wait for things, so it cannot compute things in between, and so on. So the next step in the evolution of computers were batch systems. So batch systems actually just automated what the operator was doing manually. So you could just say, first I want to compile something, then I want to link something, then I want to execute it one after the other, and to describe this along with your program, source code, binary code, and the data you want to use on a set of these paper punch cards. So where you just punched a hole when you wanted a 1 and you just left it closed when you wanted a 0. And so this mostly reduced the work the operator had to do. And here we had the introduction of first things that might be recognizable as an operating system, again, related to what we think an operating system actually is. So very often you don't need to kick out all the code when you run another job of another user, but some functionality like handling a printer, that's the same for every task, for every program that runs. So if you can leave these in memory, it takes less time to switch between processes. And that's exactly what happens in batch systems. So common functionality was actually collected in libraries. These libraries were resident in memory on the computer, and then a program could call these libraries and use common functionality like, well, printing a page or saving something to disk or whatever. Now, still in a batch system, one task ran after the other. And if a task would perform lots of I/O, we know that this I/O is much, much slower than the processor, even back then. So I/O was very slow. So for example, a paper tape reader reads about 30 characters a second. That's not that fast. Maybe you can type faster, I don't know. So even if those old CPUs weren't very slow, the difference in speed between the I/O and the CPU was very big. So when the program was waiting for I/O, the CPU cycles were wasted because it was just sitting there, twiddling thumbs, waiting for the I/O to finish before it could continue. So the processor was idle lots of the time. And back then, computers were expensive in the hundreds of thousands or millions of dollars. So you didn't want to let this go to waste. So in the mid-60s, computer scientists introduced multi-programming. So we started to split up the resources in our computer among several tasks running at the same time. Now, at the same time on a single processor, this isn't possible because a processor can exactly execute one instruction at a single point in time. So what is done is that the computer switches relatively rapidly between these activities, and especially switches between activities when one process, one task starts to issue an IO command or an IO operation. And then we know this can take a while. So we'll switch over to another process, another task that can actually usefully make use of the CPU, so to calculate something. And then when this IO is finished, we can switch back. So multi-programming essentially was still an offline system where you submitted tasks before, your operator took care of putting them into the computer, but you utilized the computer hardware better. And then a couple of years later, when the peripherals were more cheaply and computers had more memory and more computing power, then we had interactive computing, what we call dialogue computing. So essentially then you sat, like today, at your keyboard with a screen, you could type in commands, you could start programs whenever you wanted and not only when the operator wanted it. You can kill programs, you can directly see reactions to your input. So you can write something like a calculator, which would be simple, where you input a formula, type return and get the output. And since we already had functionality to switch between different tasks, we can extend this so we can interactively use the computer at the same time for many different users, each sitting at his or her own terminal, so a screen and a keyboard connected over a serial line, or maybe connected remotely even over a modem, which was very common even in the early 1970s. And essentially dialogue computing is what we still have today. Usually we have so many computers that each of you has at least a couple of computers available, if we include mobile phones and tablets and stuff like this. And still this mode of operation continues to work in the same way. So we ask the computer to do something, we enter a URL in a web browser, for example, and then we can see the result. Okay, now here's a question related to the CPU and I/O. Where in the computer does an I/O operation occur? So an I/O operation is usually handled by a special piece of hardware that we call, well, an I/O controller, for example. So when you look at an older PC, so a desktop PC, usually you have the motherboard, and the very early PCs, on that motherboard, there was only the CPU and a bit of memory, so a RAM, and a bit of ROM, so containing the BIOS or firmware, and very primitive I/O, so usually a keyboard controller, but let's ignore this. And all the other I/O had to be added using add-on cards. So plug-in cards today would be a PCIe card, and these PCIe cards, or these plug-in cards back then, were not PCIe. Those were available for lots of different functionality, like there was a graphics card, very primitive graphics card, obviously, that just displayed some pixels in monochrome. There was a disk controller, which contained a separate chip. And there was maybe a sound card, stuff like that. And each of this is a separate functionality, a separate chip in your computer. And these are connected to your processor on your mainboard using what we call a bus system. So a bus system is just a bunch of wires. And these wires have three sorts of functionalities. First, there's the so-called address bus. So an address bus, like an address of a house in the street, identifies one individual of your very many memory addresses. So we could say at address 1000, we have our graphics card. At address 2000, we have our sound card. At address 3000, we have our disk controller. And at address 10,000, we have our RAM in our computer. Then we have a data bus. So when you address a device, you need to exchange data. You need to write data to the disk. You need to read data from the disk. So this is done using the data bus. And additionally, you have the control bus. So these are lines indicating the current operation. For example, if you want to read data, if you want to write data, or we've also seen interrupts. So a device can generate an interrupt when an operation is finished. So does this give a bit more background that you expected? Or was this not what you expected? Or is there a further question? Just type it in the chat or. All right, thank you. Okay, so yes, if there's anything, I'll try to watch the chat in parallel. I hope I don't forget it. So just feel free. It's better than to just start opening the microphone with like 80 people present in Zoom. That usually doesn't end very well. So nowadays, we still use some sort of dialogue computing, no matter if it's your desktop PC or your mobile phone. They mostly work the same way, though we usually don't have multiple real world users on your computer. But don't forget, you're running code today if you have a web browser, for example, JavaScript code from a web page. And this is code you don't know, you have never installed on your computer. So this is code from someone else running on your machine. So you could say that there's someone else using your computer. And you've maybe seen all these malicious web pages that tried to run something like a Bitcoin miner on your computer while you were reading the web page or stuff like that. So also these are things that an operating system might want to avoid. So there's another question: did dialogue computers use one or multiple CPUs? So the first ones really only used one CPU because CPUs were very expensive. And so you had to switch the CPU between different users. And we'll go into detail later on when we talk about processes and process switching. So you can see how this is done. And this is a quite complex operation that you have to get exactly right in order not to crash your computer. But of course, you can, in theory, build dialogue computing with one CPU for every user, but that back then, when that was invented, that would be expensive pretty fast. Nowadays, you can buy a 48-core AMD system for relatively cheap money, so that would be okay. But then again, yes, maybe it's overkill for most applications because most people don't use the capabilities of their computer to the full extent. Mostly the computer is running idle and just waiting for the user to do something. So sharing a CPU is in general a pretty good idea. So we've seen a simple model of a computer that consists of mostly three major components: a processor or more processors, memory, and I/O devices. And I already mentioned it's interconnected. All these are interconnected using these buses. And we've already seen that waiting for I/O operations is just wasting time because you just check and check and check. It's the same like if you order a pizza and you wait for the pizza in front of your TV because you're hungry, but your doorbell is broken. So when your doorbell is broken, you have to check the door like every 30 seconds if the pizza delivery person is coming. And of course, you're running from the TV to the door and back all the time, so you don't really notice what's going on the TV, and you're mostly wasting the time until your pizza arrives. A working doorbell is something like an interrupt. So you can watch your favorite TV show until your pizza arrives, then the doorbell generates an interrupt. You're notified because you can hear the doorbell, and then you can answer the door. When exactly your pizza has arrived, you can have your pizza and eat it too. So that's a very simple model, obviously, of how interrupts work, but it's actually a quite good comparison. So the opposite thing of interrupts is what we call polling. So polling is really checking all the time in a loop. Has something happened? No. Has something happened? No. Has something happened? Still not. Has something happened? Finally. And of course, this is wasting time and effort. So interrupts are another method to make computers more efficient to use. And we've looked at a very simple model of instruction execution. So we know that the instructions that we program in our high-level language like Java or C are not the instructions your CPU understands, but your CPU understands much simpler instructions, so-called machine instructions, that have very simple operations like adding two numbers or comparing numbers or jumping somewhere. But there's, for example, no instruction in most CPUs implementing something like a loop or a function. So the basic idea is that one machine instruction is executed after the other. Now, this is a simplification that has worked for like 1970s, 1980s computers. And we've also looked at more realistic computer models today, which have multiple processors or processor cores, maybe different sorts of memories, so not only RAM, but also cache memories. And also maybe if you have several processors, you have this memory split between your processors. So accessing memory that's attached to another processor is much slower than accessing your local memory. And this is what we see on the right-hand side, this so-called memory hierarchy. The problem is that Memory speed does not grow as fast as CPU speed, so the CPU would have to wait for memory. And this is why you implement smaller, but much faster memory levels in between, like the L1 and L2 cache you see here, in order to create the illusion to have a fast and big memory, which you don't have. So there's another question. How does a polling actually happen? Reading an address in the device's address space. Exactly. So there's an address, which is usually a status register of a device, like a disk controller. And there's a bit in it that says ready. So you really read this memory location, then check for exactly that bit. And only if that bit is like 1 indicates ready, then you continue. If it's still 0, then you go through that loop again, read that memory location again and again and again until it's finally this bit has the value of 1. That's exactly how polling works. And we will have example for this later in the course. So another question is the multiprogramming context switching model for processes analogous with threads? That's a good and a complicated question. So yes and no. So essentially, if you have multiple programs, usually these programs should be completely separate. So one program or a program that's running, we'll discuss this, I think in the slides this week, actually, on the videos. A program that's running is what we call a process. And one process should not be able to read or write the memory of another process. For example, let's say you have a web browser running some JavaScript application that you loaded on some web page. And then you have your online banking application where you just handle your credit card number and whatever, and your PINs and so on. So obviously, this JavaScript code running in your web browser, this cannot be allowed to read out your credit card number and your PINs from your banking application. And of course, it can definitely not be allowed to write something in that other process's data. So it could override, like if you want to make a transaction, you want to send money to some other account, it could check for it and then override the recipient's account number to send it somewhere else. So this is what happens between what we call processes. Now, multi-threading means usually we have a good definition of threads. Threads means we have parallel activities that share memories, so that share an address space. So for example, you can do matrix multiplication in parallel by using different rows and columns and having them in the same matrix operated on in parallel. But then you have no security. So usually we say that multiple threads operate on the same memory inside of a process, and multiple processes have separate memory ranges which have to be protected against each other. All right. So next question is, all I/O devices have to be fast enough to listen to the address bus and respond with data just as fast as RAM would. In early computers, yes, that was the case. In modern computers, there's a bit of what we call a handshake going on. So essentially a processor sends out a request, I want to read data from address 1000. And then the processor actually waits until this device at address 1000 and 1000 tells the processor, now I'm ready, here's your data, please pick it up. In early computers, this was all synchronous. So the I/O device registers had to be as fast as your RAM. So if you had like a 1980s home computer, like a Commodore 64, there you could really read and write devices as fast as you could access memory, but that usually meant that memory was pretty slow and not that devices were fast. Right, more questions. How about the state machine for I/O interrupts for processes and threads running ready and blocked? So this is something we're actually going to discuss next week. I think that's in the slides for this week. So this is a recapitulation of the slides from our videos from last week. Now, but still we can discuss something. But what exactly do you want to know about that state machine? So essentially, what happens is that these changes between states, these transitions between states in the state machine, these are triggered by different events. So essentially, when we have these three states ready, running, and blocked in a very general model. So a running process, there's usually one running process on a single processor system, and that's the process that is currently executing instructions on the CPU. Then there's a number of ready processes. these processes want to run code on the CPU, and they have everything they need to run code on the CPU. So all the data, for example, they need, and they just wait for CPU time to be available. And then as soon as you start an IO operation, then you move from running, because you can only start an IO operation if you run code, obviously. You move from running into this blocked state. And the interesting things regarding to interrupts is how you get out of this blocked state. So this blocked state marks a process, and it also marks internally in the operating system kernel what this process is actually waiting for. Is it waiting for a disk or a key on the keyboard or whatever, a network packet coming in? And then whenever there's an interrupt from an IO device that says, okay, here's something asynchronous that happened, the device driver for that device, so for your keyboard or for your disk or for your network card, actually notifies the kernel, oh, there's something new. The kernel checks, for example, which process is waiting for this. So for, like, if you have a graphical user interface, and you want to wait for keyboard input, the window in front receives the keyboard input usually. If you have network packets you're waiting for, you have several ports. So there might be an SSH connection for a remote login that's waiting on port 22. There might be a web server, so if a packet on port 80. So if a packet on port 80 arrives, this is handed to your web server process. If a packet on port 22 arrives, this is handled to your SSH connection, for example. And so whenever an interrupt occurs, and this condition is fulfilled for one of the blocking processes, then this process is moved to ready. It's not immediately moved to running again, because there's usually another process running already on the CPU, which would have to be preempted. So whenever you finish an IO operation, you move to ready, and then you have to wait until it's your turn so you can continue computing. So that's essentially what happens. So interrupts mostly control the transition from blocked to ready, but there's one special sort of interrupts, and this special sort of interrupts is called a timer interrupt. We'll talk about this in detail later, so if you don't understand all details, don't worry. But since there's a question, I think I should mention this. So a timer interrupt is something that happens periodically, let's say every 10 milliseconds. And this is a very simple hardware component that just counts time. And when your time's up, it generates a hardware interrupt. So your operating system is called. And the timer interrupt in the system is the basic functionality to enable the switching between different processes. So we've said that a process executes instructions. So as long as it doesn't give up executing instructions and hands back control to the operating system, it would just continue running. And the operating system can't do anything about it because it's not running code at the moment. So it can't change the behavior of the computer. So what happens is when this periodic timer interrupt occurs, the mode of the processor or the processor is switched to executing operating systems code. That's a hardware functionality of the processor. And then this timer interrupt checks, like, is the time up for that process that's currently running? And if it's up, then we'll move that process from running back to ready, because it didn't start an IO operation, so we don't need to block it. It just needs more CPU, which it currently can't get because some other processes want the CPU. And then it selects another process to go from ready to running and switches back to that process. Now, which process is still selected is a task of the so-called scheduling algorithm, and we'll discuss this in detail later in the semester, because otherwise we'll run out of time today, I'm afraid. All right, so I think we can continue a bit unless there's more questions. And if there's more questions, let me know. So today we have many more challenges. So if you have, like to, play some games with like, interesting graphics and stuff like that, you obviously have something like a graphics card in your computer. And originally GPUs, graphic cards, were made for accelerating like 2D and 3D graphics, like drawing vectors, triangles, shading things, doing hidden line algorithms and whatever. And about like 15 years ago, people found out that lots of this functionality that a graphics card actually implements. So a graphics card is essentially a large amount of very simple processors. And this functionality can be used for other things, not only for displaying graphics. So this led to the introduction of what we call GPGPUs, so general purpose GPUs, which are Yeah, a GPU that can generate code, which has very many parallel parts. This could be, if you want to decode a video, you can decode parts of the video separately. So a video is split up in so-called macro blocks, which are usually 16 by 16 pixels big. And each of these could be decoded separately if you have enough processors, and then you can accelerate it. Or you have a process that execute the same instruction set, but with different performance and energy features. Like in your mobile phone, you might have something like a so-called big little processor from ARM that has like 2 fast but energy hungry cores for like tasks like if you do video processing or speech processing. And for the ordinary tasks in the background, you have some small cores which are very energy efficient and which are just fast enough to do all the simple stuff. And you can also have like digital signal processing accelerators for doing Fourier transforms, video, and so on and so forth. And nowadays, you also have generic accelerators on so-called FPGAs, so field programmable gate arrays. So you can define the hardware in these logic components yourself. So if you're interested in this, we have several courses on this from the colleagues in the comp group. And nowadays, there's more and more special function accelerators. So we have video and image processing accelerators like video encoders, decoders for H.264 or for JPEG. And of course, very modern in the age of AI, we have many accelerators for neural networks if you want to do like object detection, image detection, and so on. So there's another question that came in. If there's no other processes in ready state, will it go to ready, then back to running, or does it just continue? Is this OS dependent? Yes, it's also a very good question. That's actually a problem, because if there's no process in ready state, then the operating system really would have a problem. Like imagine you have a system where all processes are actually blocked. It could happen that all processes start a long-running I/O operation and there's no process left in ready state. What should the poor CPU schedule to? What should the operating system select? There's nothing to select. And there's a trick. So very many, I think most operating systems implement what we call an idle task. An idle task is something very simple. An idle task, I can type it in the chat. Wait. It's just code that looks like that. So it's an endless loop doing nothing. So this is the whole code of the idle task in a very simple operating system. So this is exactly just running a loop and doing nothing inside of that loop. So this can have a block because it does not perform any I/O operations. So this is a process that would be always ready. It doesn't wait for input. It doesn't create output. So this idle task is generated as one of the very first tasks in your computer. And if there's no other tasks available to schedule to, then this idle task is running and it's guaranteed that it's also always running. Now the problem is, this is very energy consuming because essentially it's polling for nothing. It's just running in a loop, rating and wasting CPU cycles doing nothing useful. So a modern idle task looks like this. Second. So halt is a function that doesn't halt the operating system, but just stops the processor from executing instructions. Because we know when the idle task is running, no other process is there that could be running anything useful because all others would be blocked and waiting for some I/O. Now we halted the CPU, so what can we do now? Your computer is crashed, it's stopped. Now the trick is that this halt condition actually is completed and you get out of this halt condition whenever an interrupt occurs. And of course, that's exactly what also takes a process out of the blocked state. So this idle process, the second one that executes the halt in an endless loop, halts the CPU until the next interrupt occurs. When the interrupt occurs, we know we have a process that can be moved from blocked to ready. And in turn, we have a process that is ready that can be running again instead of the idle process. But if you look at very early Linux code, so Linux 0.01, I can actually post some links to the web to that piece of code. You see, that's exactly how an idle task is implemented. And that's all. It's a very simple trick, but it's very useful and efficient, I think. There have been, by the way, also some other interesting things. So the important thing is that there's no blocking involved. So no waiting for I/O devices, right? So halt just halts the CPU. There's no waiting for I/O devices. So there was one Linux version that did this here. So in an endless loop, it calculates all digits of pi, or at least as many as it could until it ran out of power or memory. So just calculating is also just using the CPU, so it's not using I/O as long as it can stay in RAM. But of course, this is wasting even more power because it's not just idling, it's actually using the CPU to calculate something. But there's fun things that you can do in an idle task. So you could essentially, if you were a really bad hacker and you would be able to submit code to the Linux kernel to change the idle task, you could change it to mine bitcoins in spare CPU cycles of all the hundreds of millions Linux computers on the world if you manage to get this out. Now, this is an idea, isn't it? I don't encourage you to do this. Okay, there's a follow-up question. If there's a process running, when its time slot runs out, will it switch to the idle task and then go back later, or will it just conclude it doesn't have any other process and just continue running the one process? Now, this depends on the operating system, really. So usually there are priorities of processes. So whenever there's a timer interrupt, the scheduler checks which processes are available, and each process has a priority. And usually the process is chosen, but that depends on the concrete algorithm. The process is chosen which has the highest priority. And obviously in such a system, you would give the idle task, the idle process, the very lowest priority you have. So it's only scheduled when there's no other task with a higher priority that could be running. But you could implement this in a different way. But most operating systems have some sort of priority that they're using for this. All right, very good questions. Thank you. Yeah, so this was a bit of an overview of what we talked about or what the videos talked about last week. The final thing was security, memory mapping, and protection. So we already noticed that if we have multiple processes, they need to share the resources of the computer in a safe and secure way. So they should not be allowed to influence the behavior of another process. They should not be allowed to access data of another process. So we need to isolate them. That's what we call it. So for example, we need to split up our main memory into parts belonging to process A, process B, process C. You need to split our disk space. There it's a bit more complicated. There we use file systems, which, so a disk is split into blocks. We'll also see how disks work. And these blocks are allocated to files. And these files are then allocated to one or multiple processes. And we have the scheduler to allocate the CPU time. Now, lots of these functionality are supported by hardware, especially splitting of the memory is supported using a technology we call virtual memory. So all the addresses that are generated by a process, so when it reads a variable, this variable has an address, or when it jumps to a function at an address in memory, all these are no longer direct addresses in physical memory, so they're no longer handed directly to the RAM, but there's a component in between called the MMU, or Memory Management Unit. And this Memory Management Unit has two tasks. First, it performs a mapping. So mapping from these addresses your processes generate, these virtual addresses, to the real physical address in memory. So to these bits, physical bits in memory where this information is actually stored that is supposed to be accessed. This is a convenience functionality, for example, because then we can just build all programs to have the illusion starting at address 0 in virtual memory and being able to access lots of memory in your computer. So in ideally all the memory space, 4 gigabytes. Most programs don't do this. So that's the idea how we can share stuff like that. And the other thing is that we don't only map addresses, but we also can protect addresses. So we can say this address is read-only. So whenever we attempt to write to this address or to execute code from that address, actually your process is terminated and your operating system is called. That's a hardware functionality of the CPU. And then the operating system can check what's gone wrong. And the problem with this is you cannot do this for every byte in memory separately, because all the administrative information you'd need for storing translations for each byte and storing protections would take up much more space than the data itself. So what's done is that memory is split up in pages of identical sizes, for example, 4 kilobytes. And these pages are the bases that are mapped. So the offsets inside of these pages stay identical, and just the rest of the address, the higher, the most significant bits, they are mapped, and these are the basis of protection. And this is actually one of the things I'm doing research on, how we can make this more efficient. Because if you only can protect 4 kilobyte pages, then if you have smaller data units, like just a single variable in your program, which may take up just 4 bytes, and if you want to protect this separately, you would waste the remaining 4092 bytes in that page. That would be a lot of waste. So what you can do is you can put several data objects like variables or structs or whatever together in one page, but then they would not be protected against each other. So you could overwrite accidentally or intentionally data. And this is something in IT security, maybe a buffer overflow. We'll take a look at that towards the end of the semester. And this is actually the reason for most of the security bugs, even in today's computer, such a buffer overflow. For example, in C, where you write over the end of an array or a string, is still responsible for about half of all the security bugs in computer software today. We'll discuss this, and I'll show you details on how this actually works in detail later this semester if you're interested. So what we want is more fine-grained protection and mapping, but we need to find a compromise between the granularity, how small can we go, and the efficiency here. But we'll talk about this in detail later and how to accelerate this. That's an interesting question also. Is memory exploit a security flaw on OS or application level? Depends. So on the one hand, if the operating system cannot protect things smaller than 4 kilobyte individually, then it's actually a hardware problem, which can only be solved if we split data separately. So that might be done by a compiler actually. So a compiler actually decides in the end where data ends up in memory. Usually compilers don't consider this for efficiency reasons. So this is a question that doesn't really have a definite answer. It could be both, but usually it's most of the memory buffer overflow things is actually a design flaw in the programming language like C, which allows this. But we'll talk about implementations of this later, and I'll give you examples because I think that's interesting. And I think all of you should have a bit of a background also on this level, how security works. If you're interested in this, I have a course on operating system security. Unfortunately, there's 2 problems with this. Currently, it's on my private server, which I just reinstalled, so I need to get the web server up and running again. That's probably something on next week. And the other problem is I taught this course in Germany a couple of years ago, and it's in German. So that might be a bit more problematic for you. But still, I can send you the link as soon as that is up again. And the slides should be sometimes, I know for me, I can read Norwegian easily because I speak English and German. I suppose the other way around, if you speak Norwegian and English, you might be able to understand lots of German. I would be interested to see if that works actually, but it'll take a bit of time. Kein Problem. Wonderful. Vielen Dank. And I can send you links to this. So this course was an advanced course for 4th year students actually. But if you're interested, of course, as I said, I'll send around the URL next week when I have that web server up and running again. So this starts with what's a program actually, how this is transformed into a process. So how does a program on disk look like? So there's special formats like the so-called ELF format you've maybe heard about if you used Linux before, or Windows has a format called COFF, C-O-F-F. And then we look at how this process is actually loaded into memory and started, and how it's behaving at runtime. And then all the typical security problems, and it's ending up with really nasty things like code that modifies itself while it's running, so-called self-modifying code that rewrites the instruction opcodes. And so that's something we don't do in this depth in operating systems because we don't have time. But of course, I'd love to give you links to this. And this exam for that course I taught here in Germany had still my most favorite exam question of all the times. So there was half a page of hexadecimal bytes and just the question, what's happening here? And then your task was to decode the bytes, to check out the opcodes. Of course, you got a table, you didn't need to remember these. And then you needed to figure out what these machine instructions are doing. And they were doing a calculated jump to an address that was calculated by some arithmetic operations. And then it modified an operation to jump over something else. And of course, in the end, it outputted the number 42. What else? And students actually liked this because this was a bit of a challenge where you have a puzzle and something like this. So I mentioned to the department several times, we need courses like this, but you know, it's difficult to introduce specialized courses, unfortunately. And of course, we have a separate department dealing with security. That's a bit of a strange thing, in my opinion. But nevertheless, talk to the department if you're interested in things like these. I guess that's a good idea. As I said, this course is in German only, so it might be problematic for most of you, but still, if you try to translate it and have questions about it, feel free to ask me. It'll take a couple of days until it's up again, because just reconfiguring a Linux system, this old server ran Debian 7 that was probably so full of security bugs that I had to reinstall it, and so that takes a bit. So yeah, that was a quick overview of last week. So how do we go on? So the videos for this week are available since Monday. So we'll go into some of the first details like processes and process models we've seen. What you're going to get this day on this week on Friday is the first theoretical exercise. So this will be a PDF with some theoretical questions. This is optional. You don't have to hand them in. This is not graded. But still, if you want to have it graded, please submit it until next Friday. I'll announce this on Blackboard separately on Friday, so you'll get a message about this. And then, of course, you'll get your first practical exercise. And as I said, the practical exercises are mandatory because they form part of the grade. So we'll have 3 practical exercises, and altogether they form 50% of your final grade, and the rest is the exam. So the handout for this will be next week, Monday. And you'll have more time to work on this. So the submission deadline is plus 3 weeks. So the 21st of February would be the submission deadline. And if it's too complicated or if it takes too much work, let us know. We still have some headroom for deadline extensions, but of course, I don't want to announce them right away. And we'll give some hints and questions also for the first practical exercise and for the theoretical one in the live session that then takes place again next Monday in the usual lecture slot. Sorry, this Monday I was in a review session for a German research program, which ran from 1 o'clock to 9 o'clock in the evening. And then we all had to go out and drink some beer because we couldn't stand it anymore. Okay, will the practical exercises be letter graded? No. What we'll do is, because letter grading would create some round-off problems, what we'll do is you get percentages on the practical exercises. So for example, you have 80% on the first, 70% on the second, and 90% on the third one. So the overall would be 80%. And then the exam also gets a percentage, like you have, for example, 80% on the practical exercise and 70% of the exam. 50-50 means your overall percentage would be 75%. And this will then be translated to a letter grade, usually according to the usual schedule of the amount of percent you get. News about the form solution. Sorry, no, that takes a bit longer. I hope we can get this sorted out this week. But this week has been extremely busy so far, unfortunately. So that takes some time to negotiate, I'm afraid. So, but I'll obviously send an update, because a forum would be really good to have as soon as the first exercise is out, obviously. I'll send an update as soon as I know more. And if we can't find an alternative, we'll just go for Piazza and we'll pay for it again. That's life, I guess. Do we have to deliver all practical exercises? That's another question. You don't have to, but for the practical exercise you don't deliver, you get 0 points. So your average goes down significantly. Is passing the exercise alone implies passing the course? Yes, we already had the question last year, and that's an interesting question. Since it's usual that you pass an exam with 40%, I guess that would work, but you would end up getting an E. So that's not the ideal situation. And for formal reasons, That's something that, because it's more complicated, you still have to submit at least an empty exam paper. So you have to participate in the exam, but you can submit it empty. That would work, but of course I can't recommend it. All right. So that's all from my side today. If you have any more questions for now, feel free to send me an email. And otherwise, I'll send you the first theoretical exercise on Friday, and we'll meet again next Monday, I guess. So I should be back in Scandinavia next Monday from Germany if they let me back in again. But of course, it will be a Zoom session, and let's see how the Corona situation develops. I'm planning to be back in Trondheim in early March for the Catch ED event, if it really takes place in person, I hope. And maybe we can reserve a couple of hours for like just consultation. So if you want to meet me in person and discuss things, we can make something like this available. But this is not completely sure because we don't know if Catch ED actually takes place. And on the other hand, of course, I can only recommend Catch ED. It's a really nice event. It didn't happen last year due to Corona. It happened the year before in February. It was in the, I think, the Clarion Hotel next to the Fjord, and with live music and interesting talks and great buffet and stuff like that. So it's nice. Will you be teaching at NTNU for more semesters? That's a very good question. Now, that's the reason I'm currently in Germany. I can be open about this, I think. So I currently have an offer for a full professor position in Bamberg in Germany. And that's why I'm here to negotiate about this. And that's what I did yesterday. Since NTNU didn't want to offer me a full professor position, well, obviously sometimes it's good to go where the money is. That's if you don't like this, feel free to tell this the department, I guess. Okay, System D versus Init. I just talked to a student here in Bamberg in Germany, so a student of the student organization in computer science. So that's the university that offered me that full professor position. And he's responsible for operating the Linux machines of the computer science students organization. And we had a long discussion about this. Personally, I don't like System D because it's against Unix philosophy. So Unix philosophy is to have programs or processes doing very simple tasks and then combining them. System D tries to do everything at once, and it very much reminds me of the Windows registry. If something goes wrong with this, your computer just won't boot up again. But that's a philosophical question. I'm using Unix for 30 years, so this is newfangled stuff nobody needs, but maybe I'm just an old fart. I don't know. Feel free to use System D. I try to avoid it. And Init and System 5 Init is not optimal. So there was reasons to replace it, but maybe not in the way it's done at the moment. But for all the others who are not into Linux, you're not supposed to understand this. That's a very famous citation of one of the Unix books. I'll show you this later in the semester. Okay, so thanks very much for listening. If there's anything, let me know. Have a good time and see you again next week. And I'll publish the video later this evening because I guess this evening we'll have to go for a beer here with some of my former colleagues. All right, have a good time. Thank you.